In Algebra 2, you learned about a variety of different functions, parent functions to be more exact, and their properties. Let's review some of those properties here. Let's first start off with the identity function. So y equals x, we know that's just a linear equation, so that's just going to give us a line. In terms of the table, it's basically y is x, so all these values are going to be the same. Okay, which means when we graph it, you have 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. And then we can go ahead and connect those dots with a line, like that. Okay, so we have a linear equation, a line. In terms of the graph domain, let's look at the properties now. The domain is all the possible x values. So your graph keeps going to the left and also keeps going to the right. So therefore our domain is going to be negative infinity to infinity. The range is talking about all the y values. Well, the graph keeps going down and the graph also keeps going up. So there's no restrictions to the range either. Your range is going to also be negative infinity to infinity. Where does the x-intercept occur? Where does the graph cross the x-axis? Well, it crosses at 0, 0. Okay, so our x-intercept is going to be at 0, 0. And the same thing goes for the y-intercept. It crosses the y-axis at the point 0, 0 as well. So that's our y-intercept. Does this graph have symmetry? Well, notice that whatever we do in quadrant 1 is actually kind of mirrored over onto quadrant 3. And that shows you symmetry with respect to the origin. Okay? The interval in which the function is decreasing. When is the graph in a downwards motion? It doesn't look like the graph ever goes in a downwards motion. It's always going up, 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 up. Okay, so this one we can say none. There is no interval where the function is decreasing. Where's the function increasing? Well, that's everywhere. So the function's increasing from negative infinity to positive infinity. Do we have a local max or min? Do we have a highest point or lowest point on the graph? No, we don't. This graph keeps going down. So whatever point you choose, there's always something lower to the left. There's always something lower to the left. There's always going to be something lower, so we don't have that minimum. And the same thing goes for the maximum. There's always something more to the right, something more to the right, and so therefore it gets higher and higher, so there is no local max or min. If there is no local max or min, then it also goes to say that there's no absolute max or min as well. So none. Okay. Let's try another one. Which one should we do? Let's do a square function together. Okay. So when we type in, or when we plug in some values into the square function, negative 2 squared will give us 4, negative 1 squared will give us 1, 0 squared gives us 0, 1, and 4. And we know what that looks like when we graph it. We're going to get a parabola, 2, 4, negative 2, 4. There we go. Okay, and then sketch your parabola out. There we go. Sorry, it's kind of hard to draw on this. Here we go. Okay, so there's our parabola. Just make it, make it a little bit cleaner. All right, there we go. Okay, so let's look at the different characteristics of the square function. In terms of the domain, what are all the possible x values? Well, the x values start way over here, right, at negative infinity, and it works its way over to positive infinity. Okay, in terms of the range, what we're looking for are all the possible y values. Well, the y values only start here and work its way up. So therefore, our range is going from 0. Now, because 0 actually can be included, we want to make sure we do this with closed brackets as we do interval notation. So 0, and it goes all the way up to infinity, and infinity is unbounded, so we still leave that as parentheses. Okay. All right, what are our x-intercepts? Well, the x-intercept occurs right there at the origin, which is at 0, 0. And the same goes for the y-intercept. It's at the origin, which is at 0, 0. Is there symmetry? Oh, definitely, right? We have this line of symmetry going down the middle, and so this is going to be symmetric to the y-axis. Where is this function decreasing? When is it going down? Our graph is going down from all the way over here, right? And it works its way down until you reach that point at 0, 0. So that's when it's decreasing. So in interval notation, we say that this is going from negative infinity and it stops at 0. Do you want 0 included? Yeah, right? So we're going to say closed bracket for including 0. Where's the function increasing? Well, that's just on the other side of the parabola. It starts at 0 and works its way up. So we say we start at 0, close bracket, and works its way up to infinity, like that. Okay. Now let's look at the local max and mins. Is there a local max? Well, this graph keeps going higher and higher. There is no maximum that we have here. Does it have a minimum, though? We do have a minimum occurring at 0, 0. Okay, so our min is occurring at 0, 0. That's going to be our local min. And as a matter of fact, that local min is the lowest of the low. You can't go any lower than this point. So that local min is also the absolute, local and absolute minimum. Local and absolute minimum. So that's going to be the same point at 0, 0. Okay. Let's see what else we got here. I'll leave you to do the ones that we're leaving blank here. Why don't we go ahead and give the cube root a try here, okay? So let's plug in cube root of 8. That'll give us negative 2, negative 1, 0, 1, and 2. Okay, so when we plug those values in, let's see what we got here. Negative 8, it's off the charts, but we're going to be at negative 2, like, let's say right around there. And then we also have negative 1, 0, 0, 1, 1, and 8, 2 is somewhere over there. Okay. As you can see, this graph kind of forms like an S shape to it. So just form that S shape, like that. And let's look at their properties. The graph does keep going on and on in both directions. So in terms of the x values, it goes from negative infinity to infinity. That's our domain. Our range, this graph is getting lower and lower and also higher and higher, even though it's going at a very slow pace. It doesn't have any kind of limit, so therefore we can say that the range is still going from negative infinity to infinity. Okay, x-intercept, when does a graph cross the x-axis? Oh, it's at the same point of 0, 0, the origin. And same goes for the y-intercept at 0, 0. It crosses the y-axis at 0, 0. Does this graph have symmetry? Yeah, this is actually kind of like our first example of the identity function, where whatever we see in quadrant 1 is being replicated over to quadrant 3. So again, this is going to have symmetry about the origin. Interval, the function is decreasing. Is the function decreasing at all? Well, for every point you have, as you go to the right, as x gets larger, the y value is always getting larger as well. So for that reason, this graph is always increasing. So this is not going to be a decreasing function anywhere. The function's increasing at every single point along this graph. Every x value that gets larger, y gets larger as well. So therefore, this is everywhere from negative infinity all the way to infinity. Does it have a local max or min? Is there a highest point anywhere? Do we have any hills, any humps that occur anywhere along this graph? No, it doesn't go back down. It doesn't go from increasing to decreasing anywhere. So there are no maxes or mins, no local maxes or mins, which also means that there's no absolute max or mins here either. Okay. All right, what else can we do? Let's do the reciprocal function together. So with the reciprocal function, when we plug in negative 2, we'll get negative half. We'll get negative 1. 1 over 0 is undefined. 1 over 1 is 1, and 1 over 2 is half. Let's graph that. So at negative 2, you're at negative half, right there. At negative 1, you're at negative 1. And 0, we're at undefined. So we can't have that. We can draw an asymptote there. The graph does not exist there. And we also have 1, 1, and 2, half. If this graph is really weird to you, you can plug in some more points. Let's say you plug in right in here. Let's say you plugged in negative half. Then if you do 1 divided by negative half, that's the same thing as negative 2. So the x value will give us negative half. The y value will give us negative 2. So negative half, negative 2 is down here. And you can see a little bit better what the graph is doing. If you do the same thing on the other side, half will give you 2. Okay? And so the reciprocal function, you know what, let's give Let's give another one a try. No, that's fine. That graph is fine. So what we see here is that graph is coming down, wrapping closer and closer to that asymptote. Oh, that's horrible. Let me do that again. It's getting closer and closer to the asymptote. And then it comes back down like that. And then as it gets closer to the x-axis, it just gets really, really close to it, but it never touches it. You can't ever get a value of 0, right? You can't ever have a y value ever equal to 0 because that 1 is always going to be a little bit more or a little bit less than the value of 0. And for the same reason on the other side of the graph, this graph wraps towards the asymptote. It never can get to infinity. And as you go down, you can never get to 0, right? 1 over 1,000, 1 over 1,000,000, you'll never have the value of 0. So we also have a horizontal asymptote occur at 0. Oh, that's a horrible graph there. But you get the idea. This is called the reciprocal function. Okay? In terms of the domain, what can the x value be? Well, the x value starts way over here. You can start at negative infinity, and you can keep going and going and going. But are there any x values that can't exist? Yeah, definitely. We see that there was this vertical asymptote right in the middle. So you go from negative infinity to 0. You don't want to include the 0 because you can't have 0, which means we do open parentheses saying you don't include 0. Union, and then we again keep, let me rewrite this, it's a little bit messy. Negative infinity to 0, union, and then where do we start? We start back at 0, don't include 0, and work your way over towards infinity on the other side. Okay, so this is basically saying that the domain is all x values, all real numbers, except 0. You just can't include the 0 value. Okay, what's the range? Well, in the same manner, you can go all the way from down below, negative infinity, work your way up. The graph has all the y values that exist here, all the way until you reach the y value of 0. So it's actually going to be the same thing, negative infinity to 0. Don't include 0 because you have that horizontal asymptote, and union started at 0 again and go all the way up to positive infinity. Okay. Do we have any x-intercepts? Does the graph ever cross the x-axis? No, it doesn't. Does it ever cross the y-axis? Do you ever get a y-intercept? No, it doesn't. So we say none. Does this graph have symmetry? Yeah, it does, right? We have symmetry. We have lots of symmetry, actually. This symmetry occurs with respect to the origin. And also, if you were to mirror this along the line y equals x, you can see that this part folds over to this part folds over to this part, so this also has symmetry about the line y equals x. Okay. Where is this function decreasing? Well, the graph is decreasing as x gets larger, y gets smaller. As x gets larger, y gets smaller. As x gets larger, y gets smaller. It's decreasing on this interval here, right? Which is going from negative infinity to 0, non-inclusive. You don't want to include the 0 because, again, you don't have 0 on the graph there. Okay. Where is the function increasing? Oh, wait, it's not increasing anywhere. This is still decreasing, right? As x gets larger, y gets smaller. As x gets larger, y gets smaller. So, in fact, you have union 0 to infinity. It's basically decreasing everywhere, which means if it's decreasing everywhere, it's increasing nowhere. So this doesn't have any increasing area. Okay. Does it have a max or min? Do you have a highest point or lowest point? Well, unfortunately, as you go from this point over a little bit left, it gets higher, it gets higher, it gets higher, but there's no maximum to say that it's going to go down at any point. It just keeps getting closer and closer to the asymptote. So there is no maximum here. Same thing over here. As we get higher and higher, right, there's no maximum. You're not going to reach a point where it says, okay, that's the highest point. Okay, so there is no max. And how about mins? Are there any local mins? Well, this graph keeps getting lower and lower and lower, but you don't have a point where you can say, that's the lowest of the low, right? I can't go any lower than that. It's not like that. We keep going lower and lower. Same thing here. We keep getting lower and lower, even though it looks like we're going to reach 0. Again, we're never going to be able to touch that asymptote, so you always have something a little bit lower, and yet we never reach 0 either. So there is no minimum here either. So there's no local max, no local min, which also means no absolute max, no absolute min. Okay? All right. I think that's enough for the parent functions. I'll let you do the rest, okay? Actually, maybe we should do the greatest integer together. That's a good one. Okay, so the greatest integer function, let's change colors here. So the greatest integer function, you may see it typed out like this, or you may also see it as something like this. Okay, so this is how you can also rewrite the greatest integer function. You might see that in your book. Okay, so you see like a kind of like a bracket with a line through it is the greatest integer function. Okay, so what it means is if you have a value in that greatest integer, let's say the value of 1.3, so if greatest integer of 1.3 like that, then basically that's saying that you have anything that's less than or equal to that value. So this is going to basically be brought down to its greatest integer of 1. Okay, so if we plug in some values here, let's say -1, well, we'll just get -1. If we plug in -half, okay, we're going to make it brought down to its greatest integer, which will be -1. -1/4, same thing. It gets brought down to its greatest integer of -1. You always bring it down. Okay, 0 will be at 0. 1/4, it hasn't quite hit its integer value, so it's going to get brought down to 0. Same thing with half. You haven't reached an integer yet, so therefore you get brought down to its greatest integer, which is 0. Same thing with 3/4. And then 1 is now an integer. It's going to be its smallest integer of 1. 1.5, you haven't reached the integer of 2 yet, so it gets brought down to its greatest integer of 1. 2 is now at 2, and 2.7 gets brought down to 2. 3 is at 3, and 3.2 gets brought down to its greatest integer of 3. Okay, so we have our values here. Let's go ahead and plot those. At -1, we're at -1. Zoom in on this, makes it easier to graph. At -half, we're at -1, so -half is at -1 like this. Okay, -1/4 is also at -1. You can see basically you're creating this kind of a horizontal line. Once you reach 0, though, now you're at 0. Okay, at 1/4, you're right here, 1/4, you're going to be at the value of 0 still. Okay, and so basically you get another horizontal line all the way until you reach the value of 1. Okay, at 1, you're actually at 1. 1.5, you're still at 1. Once you reach 2, you're at 2 now. At 2.5, you're still at 2. At 3, you're now at 3. At 3.5, you're still at 3. So it looks like this. Okay. Now, to be clear, these aren't the only points. You also have like the value of 1.9, right? 1.9 gets brought down to 1, all the way until you reach the value of 2, but you know that 2 can't actually be part of that greatest integer of 1. Oh my gosh, Kaden. What? Okay, let's resume. Sorry about that, guys. So at 1.9, we're at 1 still, but once we reach 2, you can't include the value of 2, so we're going to give that as an open circle, saying 2 is not part of this value. So what you create is what's called a step function, where it has a closed interval at the starting value and an open interval at the ending value of each of those steps, because you don't want to include that next integer. So what you create is a graph that looks something like this. Okay, you create these steps. This is called a step function. And notice how the step is basically closed on one end and open on the other end. That's what the graph looks like, because that next integer is going to go at the next higher step. Okay, so that's our greatest integer function. There are some questions that are down below to help us understand this more. It says sometimes the greatest integer is called the step function. We just said that. Why do you think that is? I wonder why. Maybe because the graph looks like steps. It resembles steps. Okay, is the greatest integer function continuous or discontinuous? Well, if the graph is continuous, then we're saying that the graph keeps going on and on, right? There's no breaks in the graph at all. However, in our graph here, we do see that the break occurs at every single integer, right? The graph has breaks there. Basically, if you can think about it this way, if you have a graph and you put your pencil on the graph and move your pencil along the graph, can you draw along the graph without lifting up your pencil? If you can draw on the graph without lifting up your pencil, we call that a continuous function. If you have to lift up your pencil to go on to the next part of the graph, then it is discontinuous. So in this case, because we have to lift our pencil up every single time at each integer to get to the next step, this is going to be a discontinuous graph. Because the graph breaks, or the function, I shouldn't say graph, the function breaks at each integer. Okay, all right, we'll stop it there.